Welcome back, everybody. In this video, we're continuing with section 5.1. We just got done looking at what a discrete probability distribution is and a couple of examples. And we've been looking at formulas for finding the mean and variance for a discrete distribution. So that's where we'll start here is with another example. So for this one, we're going back to the example earlier we'd had with the sociologist surveying households in a town. The random variable x represented the number of dependent children in the households. And so we had to fill out the 0.22 before was the point of our earlier example, but now we've got it. So we're going to find the mean and standard deviation of this distribution. So that's the purpose of this one. So for the mean, we just need x p of x. So let's do that. So mu will be the sum of x p of x. So I'm just going to multiply 0 times 0.07. That's kind of pointless, but I just want to make sure we know what the format is. 1 times 0.20 plus pattern continues all the way down to 4 times 0.13. Okay, so let's see what we get. All right, so going through the calculations, we end up with 2.14. So before we continue, I want to make sure that we're clear on what exactly that means. So we've determined that if the sociologist goes and visits households, there's a 7% chance there's no dependent children, a 13% chance that there's 4 dependent children. If the sociologist keeps visiting households, the long-run average number of children in a household will be about 2.14. That's the long-run average. Some more, some less, but over time, the average will get close to 2.14. Okay, so then the next thing, we want the standard deviation. So I'm going to find the variance first, and then we'll just remember to take the square root at the end. So now we need the sum of x squared p of x minus mu squared. Okay, so x squared p of x. So 0 squared times 0.07 plus 1 squared times 0.20. That's not very exciting so far. 2 squared times 0.38. 3 squared times 0.22. 4 squared times 0.13. There's the x squared p of x's. And then we're adding all those up, and then we'll subtract the 2.14 squared. That 2.14 is what we calculated just a minute ago. All right, so let's see how this variance comes out. Okay, so going through the arithmetic, the variance worked out to be about 1.2. So to get the standard deviation, we're going to take the square root of 1.2, and that works out to be about 1.09. Okay, all right, so we've got the mean and standard deviation for the number of children that the sociologist will run across. All right, so that takes us to the end of this example. So far, we don't have a concrete, like really interesting meaning for that, other than that a bigger standard deviation would be more variable. We're going to put some meaning on that really soon. All right, so when we're working with the mean and standard deviation, we have a round off rule for that. So that's shown here. When you're finding the mean, variance, standard deviation, round results by carrying one more decimal place than the number of decimal places used for the random variable x. So remember that what we're finding is the mean value of x or the standard deviation of x. And so however many digits x has, use one more digit in our mean, standard deviation, and variance. Specifically, if x values are integers, as they have been so far, then each of these will be rounded to 1 decimal place. So coming back to here, it would make most sense if I rounded each of these to 1 decimal place because the number of children was a whole number. So let me call this 2.1. And then this one is already in tenths. This one I should round it probably to 1.1. All right, so 1 digit more than the number of digits in our x. Okay, next thing, expected value. The expected value of a discrete random variable x is denoted by E for expected value, and is the mean value of the outcomes. So note that E is the same as mu, called by another name. The mean of a discrete distribution is the same as its expected value, also called its expectation. Expectation is the mean also. E can be found by evaluating the same formula as before. Okay, so just a quick example. Suppose that we roll a die. We're going to let X be the number that comes up. Okay, just the usual die that you play Monopoly with. We want to find the expected value E. So there you find the sum of the x's times the p of x's. So here our x value, 1 occurs with probability 1/6, 2 occurs with probability 1/6, and so on up to the outcome of 6, which occurs with probability 1/6. Okay, so here I'm going to factor out the 1/6, and then we're adding up the numbers 1 through 6. All right, so there's 3, 6, 10, 21/6, and that's 7/2, which is 3.5. Okay, so that is the mean. That's our expected value. Looked at another way, if we roll a die, you can get an outcome anything between 1 and 6. 1, 2, 3, 4, 5, or 6. If you do that a whole bunch of times, like go home, you probably are home, sorry. Go get a die, roll a die 100 times, write down the numbers that you get, average them, and you're probably going to get a number pretty close to 3.5. That's what we're figuring out. Okay, the expected value. Okay, another example. For this one, we're going to make a game out of it. When you roll a die, if it comes up a 1, 2, or a 4, you're going to win $2 in this game we're going to play. If it comes up a 3 or a 5, you're going to win $1. Sounds great so far. If it comes up a 6, though, you're going to lose $5. Based on this, we want to calculate the expected value, and then you want to decide, we want to know if you actually want to play or not. So thinking about it, you win if it comes up 1, 2, or 4, and you're going to win $2 if that happens. In fact, if it comes up a 3 or 5, you're also going to win, but you're only going to win $1. If it comes up a 6, you lose, and you lose $5 when that happens. So when you lose more, but you're going to win more often. So what happens? Let's calculate the expected value and determine if you want to play. So here are possible outcomes. You could win $2, which I'm going to represent by a positive, as we're doing this from your perspective. You win $2, and that's going to come up with probability 3/6. I know that's a half. I wanted to leave it unreduced so that you can see where it comes from. That's the 3 winning possibilities. Getting a 1, 2, or 4, you win $2. If it comes up a 3 or a 5, which has probability 2/6, then you're going to win $1. Okay? If it comes up a 6, and there's a 1/6 chance that will occur, you're going to lose $5. And I'm going to represent that with a -5. So your loss of $5. Okay, so let's calculate the mean or expectation. And so that will be the sum of the possible outcomes times their probabilities. So X could be $2. That occurs with probability 1/2. Or $1. That occurs with probability 1/3. And then a loss of $5, that's plus -5 with probability 1/6. Okay, so let's add all that up. So 2 times 1/2 is 1. We have plus 1/3 minus 5/6. Let me change all that to sixths. Okay, so that's 8/6 minus 5/6 is 3/6, and so that is a half. Okay. All right, so take a look at that, and let's see what exactly that means. All right, so what is the fact that the expectation turned out to be a half or 50 cents? What does that actually mean to you? If we play this game, we're going to be trading money back and forth, right? If you win at first, you're going to win $2. Maybe you win again, win $1, and then maybe I win and I win $5. We're trading money back and forth by playing this game. What the 50 cents means is that if we had the money to keep playing this long enough, with neither of us running out, right? If we kept playing this for a really long time, then on average, you'd be ahead by 50 cents per game over the long term if you played a really long time. So let's say that we played 100 games. If we played 100 games, we would trade money back and forth, but by about the 100th try, you'd be about $50 ahead, okay? There's, of course, going to be some fluctuation with that. The mean is a long run thing. The expected value is a long run thing. But after 100 trials or dice rolls, you'd be ahead by about $50. That's what the 50 cents means. For every dollar risked, you'd be ahead by about 50 cents. Okay, so the second part, do you want to play? So that is a little bit subjective, but if you have the money, it's definitely in your best interest to play. The longer that you play, the more ahead you will be. Okay, let's try this one. We're going to spin a spinner, like kids' games have a little spinner. We're going to spin this spinner that's shown here, and the prizes are as follows. Yellow wins $1, green wins $6, blue wins $2, red loses $3, and black loses $1. Okay, we want to find, first of all, the expected value of this game. So pause the video and see if you can calculate the expected value for this game. And then restart the video and see how you did. All right, so this is how I would start it. So I would figure out the probabilities for each outcome. So there's 8 slices here. We're going to assume if it lands on a line, you're going to spin again. Okay, so ignore that. Yellow, there's a 3/8 chance, green a 2/8 chance, and so on, all the way down to black, which has a 1/8 chance. And so again, I'm going to represent the wins by positive values and the losses by negative values. We're going to multiply each probability by each outcome and add the results. So here we've got 3/8 and then 12/8. I'm just going to leave this all as 8s just for simplicity. The next is 2/8, then minus 3/8. And minus 1/8. Okay, so 3, 12, 2, -3, and -1. So that's 15, 17, 14, 13/8. All right, so 13/8, that's 1 5/8 or 1.625. $1.63 basically. All right, so the expected value on this one, the mean, is going to be 163. So again, if you play this for a really long time, you'll be ahead, on average, $1.63 for every turn, on average over the long term. Okay, so then the second part of the question, what is a fair price to play the game? So we haven't discussed what a fair price is, so now's a good time. What a fair price is would be the price that we should charge to make it so that the game is fair. And by fair, I mean so that neither side has an advantage. Here, for this spinner game, it definitely wouldn't be a good idea for me to play this game with you, because although I could, you would lose sometimes, right? If you spin either black or red, you definitely are going to win more and more often, right? On average, $1.63 per turn. So definitely an advantage to you and a disadvantage to me. What if I charged you $1.63 to spin the spinner? If I charge you $1.63 to spin the spinner, that takes away all of your advantage. It doesn't give me any advantage, but it makes us basically even, right? So the fair price to play the game is $1.63. If I could get you to pay $2 or anything over $1.63, it would be to my advantage. But the $1.63 is the fair price to play the game. All right, So that takes us to the end of that example, and it also takes us to the end of this part of section 5.1. We have yet more work to do, so we'll see that soon. In the meantime, let me know if you have any questions, and then have a great day.